Welcome to the HiRSE Summer of Testing. This is a collection of tutorials focusing only on testing and is a separate series to the usual HiRSE seminar series.
I'd like to welcome you to our HiRSE Summer of Testing seminar series, in which I would like to give the talk Testing with C++. My name is Georg Hammerl. I'm working at the Helmholtz Center Herion in Hamburg at the Institute of Material Systems Modeling. And I'd like to thank my colleagues Sebastian Pröll and Amadeus Geber from the Institute for Computational Mechanics at the Technical University of Munich. Let me give a short outline of the presentation. I'll give a short general overview, then would like directly to switch to C++ coding, and I'd like to focus on Google Test as well as CTest and give a small conclusion in the end. What is important about testing, and in general the question, why is testing so important? So it is something that accompanies each code development and is as essential as producing the code itself. It is crucial and helps to find bugs, but more important, it validates functionality. And it is also very important when it comes to refactoring or further enhancement of the code. And we, of course, would not like to have our old code broken. So here it is important to have valid tests. And my experience is the more people are working on a code, or the larger code project is, the more important is according testing. And it's just here said in brackets, no testing is never an option, in my opinion. There are several types of testing available, just to get here an overview. So from the smallest units, unit testing, which really focus on very tiny parts of the code, maybe a single class or single function or method. Integration testing is already on a larger scale. It's about the interaction of different modules and how they interact. System testing is then already the next step. So it validates the full system behavior, maybe also named as an end-to-end test, depending on the application. And a little bit of side of these three tests, which more or less give a hint what is the size of the part of code to test, is performance testing. It's not just about comparing the values itself, it's also about how performant these values are calculated so that there is no degradation in performance over time by changes in the code or under various workloads. And another sort of testing is acceptance testing, so where it is checked whether the expectation of the users are met. What is important for all of these testing scenarios is it should run on a regular basis and it should be automated. This is very, very important to have a good, the base of every testing strategy. In my presentation, I will focus now on unit testing and system testing in the remainder. But before I come to the details, here are some facts that should one consider when one has to choose a certain testing framework. So this is not just here for C++ relevant, this is more for each testing setup interesting. So it should be, of course, easy to set up, should nicely integrate with development tools and the IDE, and should support us with many helper functionality, such as assertions and then mocking capabilities. The details will come later. And there should also be a lot of documentation available and community that can be asked in case there are questions. For C++, for unit testing, there is Google Test, also called gtest, one option that is widely used. Catch2 is another one, boost.test, or CPP unit. Regarding the system test, I would like to talk about CTest, which comes with CMake, which is good for system testing. So unit testing and system testing is something that will be covered in my presentation. So now let me briefly introduce Google Test. It is available under BSD3 license on GitHub. It's well documented. That's one of the reasons why I like it. So there are guides, samples available, FAQs, cheat sheet, and so on. And it nicely interacts with CMake, which we use for our project as build system. Google Test provides many assertions. This means predefined comparative functionality, as well as test fixtures. This means that code can be reused to set up or tear down certain parts of the test. And there's also a built-in mocking framework. And mocks mean that classes or functionality can be, instead of having the original class being included, a mock object, and which allows then to remove unnecessary dependencies between the tests. So here's a link where details can be found. One has to pay attention a little bit. It means that there is some additional maintenance cost involved, meaning that the mock needs to know what the original behavior is. And thus, if the original behavior in the code changes, the mock has to be changed too. So this is something that one has to keep in mind when using mocks. Now let me introduce Google testing in a little bit more detail. The main function is just very short. We can see it here. So these few lines are the base that are necessary to get gtest running. So it's the inclusion of the gtest header, the main with the initialization of Google test, and then already run all tests includes all the tests. So all the tests register themselves automatically that they run in here, and the return value in the end. I would also like to add here MPI, so message passing interface functionality, our code, RC4C, which is jointly developed at the Technical University of Munich, the University of the Bundeswehr Munich, and also my colleagues at HiRSE as well as the University of Augsburg, is based on MPI. So for us, testing in parallel is very important. And that's why I would like to show how this is included in our testing strategy. Let me start with the easiest test macro that is available in Google Test. So let me go through here. One starts with including the gtest header and the inclusion of the header where the method or function is included that should be tested. Let's open an anonymous namespace. And then the test keyword comes with the test suite name and the test name itself. Then comes this well-known AAA pattern from testing. So we arrange data. Here in my case, there is a residuum Jacobian necessary. Then during this act phase, I call myself local Newton function, which I provide with the data previously gathered. I give here the 0 for the starting point of my local Newton method and the tolerance that is used within my local Newton truncation error. Then the result comes back from my function, and this is what in this assert phase is then compared against what I expect to be the correct solution. And here it's expect near, so I give another tolerance which then compares the expected value and the actual result, and it accepts the result as good in case the tolerance is met. Now we come to a more complex version. So this now includes test fixtures. Test fixtures allow to reuse code. So there is the possibility to have a setup and a teardown method, which is called before and after each of the single tests. So here are 3 tests that should be as independent as possible, of course. So what happens is during this testf macro, first this constructor is called from our fixture class, then the setup method is called, then the test itself runs. Here one method is checked. Afterwards, the teardown method is called, and finally the destructor is called from my fixture class. Here I have manual memory management with new and delete. Usually we would have here a unique pointer. This is just to show how this works with the setup, where we allocate memory, and in the teardown we free the memory and make sure that everything is nicely cleaned up. And even if one of the tests fail, that's no problem. They're all fully independent because in each time the setup and teardown is called separately. So they do not interact, which is desirable for tests. We have seen several of these assertions now, and there is in general a difference between the expect assertions and assert. In the expect case, the run continues after the failure, and this allows to reveal more failures in a single run, which can be advantages. And in the case of assert, it fails immediately, because this is usually useful when there is no sense in continuing the run. There are different assertions available, so here's a link to more details. So for example, the general system behavior, whether something succeeds or fails, can be included. For primitive data types like Boolean string, float, or double, comparison is available, whether it's equal here or just near for the float or double, which can be very interesting to set a tolerance. If we know that it's, for example, okay that maybe 12 digits are met, but the 13th and so on are slightly different, so this can be also accepted as okay. What is also very nice, exceptions can be checked, meaning that the code throws some exceptions, and here we can check whether these are thrown correctly. So this is very helpful. And regarding death assertions, there's here just a hint about threading. So to make the whole thing thread safe, there's the option. Here's some details that can be included in the main function or into a single test run. It usually slows down the whole testing a little bit, but at the same time, it makes it thread safe, which might be desirable. These presented here are quite strict, so there is clear expectation which data types and what can be tested. On top, there is a custom assertion, expect pred, which I would like to present on my next slide. It is in a format way available, meaning that there is expect pred format, which allows to also use the variable names in the error message. I would say its advantages to use this version instead of expect pred. And in our code, we have here a macro for convenience. So we just call here custom expect near with the actual result, expected result and tolerance. And here in this case, I use a standard vector of some doubles. So this goes beyond these primitive variables. And what we use from Google Test is this expect pred format 3, meaning that there is a functor to be provided. Details will come on the next slide. And 3 arguments. That's why here this 3 is included. When the test passes, then just here this short note, and that's it. If it failed, so here I have 2 vectors, in one I changed one of the values. And now here my custom message comes, which I will show on the next slide how this is produced. If you have now a look at this custom predicate assertion, so here again on the bottom is this expect pred format 3 line, and here on top we see the functor, this assert near, that is called from within gtest. So we have a look here, there are 6 arguments. So the first argument belongs to the fourth and member and the fourth variable that goes in, and so on. So there are 3 arguments for the names and 3 arguments that provide the data itself. If you have a look now, we see that it takes the two vectors that go in, so a standard vector of some templated type. Of course, if the size is not equal, then here's such a custom assertion that is presented on the screen as we've seen on the last slide. If this is fine, we really check the details of both vectors. So we loop over them, and if there's one entry different, depending on the tolerance that we have given, then this line is finally produced as we've seen on the last slide. And here this customization can be very helpful to get more detailed results. Now, let me give an overview how Google Test is included within our framework. So our framework is CMake based, and so the project has several folders like the source, the CMake folder in which we have several functions that I'd like to present later on in detail, and this unit test folder that comprises on the one hand also the folders from the source, in which then the corresponding unit tests are included. There's also CMake lists. There's the main that we've seen before, and common folder. So this custom assertion from the previous slide, it is included here in this custom assertions.h file. And here the CMake lists can be seen as the library includes the directory, and finally the target unit test underline common, which base is on maybe several other libs, is here defined. If we have a look at the CMake lists, which is in each of these folders, then they're quite short. It's just about the test name that is specified, then which files are to be tested, and then this add gtest executable function, which we have here, is called, and these here are, for example, tests which run in parallel. So NP, number of processors, 5. So these tests should run with 5 processors, and here the source files. And then if there are further libs, or the libs that are to be linked are provided here. So for the second folder, it's very similar, except that here the gtest executable does not contain this NP part. So here we assume they run in serial with one processor. And here again, the lib from the second folder is included to test. The CMake lists within the test folder, it is very trivial. It just lists all the directories that are relevant. So this common folder, and then all the folders to be tested. So this is not that difficult, and the setup on the higher level is we include in the CMake lists file on the one hand the functions that we need. So here's the loop to include those functions which are called in here. Then we fetch the content, meaning that the Git repository is declared, and for Google tests, which one we use. And finally, there's the enable testing and add subdirectory unit tests. So here this folder is included to call all these things automatically. Now let me briefly present how these two functions that we've seen on the previous slide on the top in our CMake structure are set up. So here again, the two tests, here with the parallel version, here with the serial version, and we see both call the same gtest executable function. In the beginning, we just parse the arguments. If there is no NP defined, then we set it to 1. Then we add the executable Here it's the test name, our main, and all the files that are included. This here is just listed to see it once. It's quite nice. It's possible with MPI that just the first processor writes more detailed output. The other one is silent. So I won't go into detail, just have a try if this may be interesting for you. And then finally, the add test and settings and test properties is called, so to say, to register the unit test within CTest. But this I will go into detail also later on. Now let us have a look here at the link gtest necessary libs function. It just brings together the gtest library as well as the common unit test stuff where the custom assertion is included. So this adds the necessary links as well as here the libs to test. So far I've only talked about the unit testing. Unit testing goes hand in hand with the system testing. Here we use CTest. CTest is an executable that comes with CMake. It's also possible to use CTest without CMake, but it's nicely integrated, so I can just recommend it. Here's a link for some details. And CTest then handles to run all the tests in the project. And we've already seen now several times this add test call is the main command. It just gives the name, so the test name, and which command should be used to run. It is enabled when we have on the top level CMake lists in the project folder, this enable testing included right at the end. And here the add subdirectory unit test we've already seen. So there will be further directories included, which I will show in the next slides. In the add executable, we have already seen, so these are the main parts that are relevant to link to get the interlink between Google Test and CTest. But now let me come to the project structure when it's about CTest and how we include there our system tests. So for abbreviation, I removed here the unit tests folder and its bottom structure. So that's why I bring here also in brackets this add subdirectory unit tests and include a further folder, it's tests, and therein is the TestingFramework.cmake file. This includes some macros that are helpful to create the tests. And on the other hand, there's the file with the test list itself, which can be quite lengthy. But now let me come again into detail and present these two files, what they include. So if you have a look now at the TestingFramework.cmake file, therein are several functions defined. They help us, for example, to specify dependencies which are possible. Tests can be labeled. This can be very nice because if I only would like to run a subset of tests, then this is very helpful. And also test properties can be set, for example, number of processors, or if there is a certain timeout, then this can here be set with all the functions defined in our TestingFramework.cmake file. This is now the second part of it. This is one of the macros, how it looks like. This one is used to add the test itself, so beyond these helper things from above. So here some files and so on are set, in which directory and so on. Here's the add test, the base functionality, so our test name and what's the command that is run afterwards. Here we set some test properties. So for example, if there is some fixture relevant, and here the test cleanup that comes here on the bottom that is called after each test. So there's some cleanup which just removes the created folder. Afterwards, a label is checked whether there is one specified. If so, then this label is set. Then here we have already the end of the macro. So this is one macro. There can be several ones. This is the easiest, and I've also simplified a little bit compared what we have in our project to have here a nice overview of what it includes. Then the list of all tests is included, which are specified in the second CMake file. And here the small add test. So the cleanup is already defined as a test, which, as mentioned, clears the folder. Okay, then let me have a look at the second file, this testing framework list of tests CMake file. We've seen this macro from the previous slide. This macro is then here called in one of these single lines. So test input under line 1 is then here in our case an input file name, and it's also the name of the test itself. We have here a number of processors that it should run the test, and if there is a label, then here it is optional. We see it here, it's not necessary. It can be added. What I think is quite nice, we have some tests with a minimal label, meaning it's like a smoke test. If I change something, I can run very quickly only these minimal tests, and I have a good feeling if something is broken. And also some else label can be used to group the tests together. Here, this is just an example. If I have tests with an altered timeout that is necessary, then another macro compared to the one from the previous slide can be called. And here we specify the corresponding test time. And also subdirectories can be included if the whole structure gets too complicated. There are several possibilities how to run the tests. In general, it's always about just to type CTest, but there are several options available. So for example, what I've mentioned, the CTest-L minimal in my case would, for example, run all the tests that have the label minimal. So this can be the subsets, the smoke tests, what I've mentioned, or another example would be with my label 1 from my example, and so on. So some tests can be excluded and so on. So a certain range of tests that is run. So here are several options available. And for details, please have a look at the corresponding link here. I would like to briefly summarize my presentation. I have shown Google Test as well as CTest, how they interact nicely within our build system CMake. What is important is that tests run on a regular basis and automatically, of course. There's a lot of documentation available for those two that I have shown. There are also many YouTube tutorials available, which especially are helpful for beginner questions. And of course, there are many more sophisticated features, which I have shown a little bit of. But here, this may be a starting point for you, what I have shown. Figure out, have fun in coding, and have a nice day. Bye-bye.
Thank you for watching this tutorial. Please check out the slides on Zenodo linked below and see you next time.